This lecture looks deeper into the world of volcanoes. And while in the last lecture we kind of talked about where we can find volcanoes and what a volcano is, in this one we're going to take a look at the eruptions of those volcanoes and the different types of volcanoes that occur. And all volcanic eruptions are centered around the type of magma or lava that is coming out of the volcano. And there's two types. Number one is mafic, which is a dark magma, a dark colored magma. It's a darker red when it's melted and hot, or it's a dark red or a dark colored igneous rock. And it's dark colored because it contains lots of magnesium and iron, which are two elements from the periodic table. The second type of magma is felsic magma. It's called felsic because it contains feldspar and silica. So you got the fel right there, and sic from silica. And feldspar and silica are two minerals that contain oxygen atoms. Which tend to do certain things when they are really heated up in hot magma. So we'll hit on that a little bit more in a minute. But the mafic rocks, mafic magma makes up the oceanic crust. So this is like basalt. And the felsic rocks, with some mafic parts to them, make up the continental crust, and this would be granite. And if you think about it, if you look at a piece of granite, there's light specks and dark specks. So the light specks come from felsic areas, or felsic magma. The dark specks come from mafic magma. So because of these two types of magma, we end up with different types of eruptions. And what we're really looking at is a property called viscosity. And viscosity is resistance to flow, or I like to kind of call it stickiness. The stickier the magma, the harder it is to flow. And what we end up seeing is that magma that has lots of trapped gases, like from oxygen atoms in it, tend to produce an eruption that is called explosive. Alright, because it is very sticky. So, lots of gas equals a sticky magma, compared to magma that has small amounts of gas. So if we have magma that does not have a lot of gas, we get what is called a quiet eruption. And mafic magma has a very low viscosity, which means it is not sticky. Alright, and this is what we're seeing from oceanic volcanoes, like the volcanoes that make up Hawaii, or the volcanoes at the mid-ocean ridges. They come from mafic. Alright, so mid-ocean ridges and hot spots like Hawaii. And because it's not sticky, it doesn't like bubble like it normally would, so gases can easily escape. They don't get trapped. And so those Hawaiian island volcanoes release quiet eruptions. They are not the big ones that go kaboom. The lava can just flow out of the crack or the fissure of the volcano. Now when we have this mafic lava flowing and cooling, we can watch the lava flow right across the landscape. And if you get a chance after you're done watching this, take a quick look on Google, or even here on YouTube, just search lava flow and you'll see lava flowing. There's some pretty decent little videos about it, about lava flows out there, a lot of them from Hawaii. Now, as it cools, it starts to cool rapidly, which gives you small crystals in the rock. Alright, so again, think of something like the basalt. You couldn't really see the crystals. And the other thing you can look at is as that lava continues to flow after a crust form, it starts to wrinkle and it forms a rock called pahoho. And it forms from hot fluid lava. It's got a smooth, ropey texture. Pahoho, I think, means rope in Hawaiian or something like that. So you just get this smooth, ropey structure. It's just one way that a lava flow can cool. The other way that the lava can cool is that if it starts deforming rapidly, starts bending, or gets really, really thick, it forms a bunch of wrinkles and jagged chunks, jagged cracks, and that is called a'a. And the main differences between a'a and pahoho, alright, even though they could have the same composition as pahoho, the big difference is not only whatever dissolved gases are in there, but also the rate, which is the speed, and the slope of the lava flow. Alright, and so the faster the lava is moving, it might cool a little slower, get pushed more out of the way, and so you'll end up with one type or the other. So flow rate, which is that whole idea of speed and gas content, both affect the appearance of lava, and pretty much the faster the flow is and the higher the gas content, the more rough it is. So fast with lots of gas gives us a'a. Slow with very little gas is pahoho. And I'm just going to abbreviate it. The other type of eruption, besides the quiet ones, are the explosive eruptions. And these are the eruptions that you think of when you think of volcanic eruptions. And they come into play because of felsic lavas. Felsic lavas are very sticky, and when these volcanoes erupt, stuff called pyroclastic material flies everywhere. And pyroclastic material are rock pieces. Alright, so if we look at a continental volcano, like Mount St. Helens, the lava, or the magma, is cooler and stickier. And the big thing is these cooler, stickier lavas contain large amount of trapped gases, such as water vapor and carbon dioxide. And so what we end up seeing is, and you're kind of missing this piece, you end up seeing that felsic magma leads to explosions. The felsic magma tends to explode, and it throws out the pyroclastic material in the air. So if you take like your brother's or sister's pop bottle, shake it up for a long, long time, and then open it, all the trapped gases come flying out of it. That's the same type of thing that's happening in the explosive eruptions, except instead of having pop spilling out, we have molten super hot rock called lava getting spit out and flying all over the place. This right here is a picture of Mount St. Helens, of what happened in May of 1980. And what we ended up seeing happen here is that there was a huge earthquake. Well, not huge, but a 5.1 magnitude earthquake that right here, where number 1 is, caused this crazy landslide. And like a big chunk of the mountain just kind of melted down in this giant avalanche, or giant rock slide. And what had been happening for, a year or so before is that there was this bulge that kept occurring where all these gases were building up and pushing the rock out of the way. That's how big the pressure was. Well, when this earthquake happened, a small hole happened in the rock, and that pressure was released, and it sent out a 17 to 18 mile fan-shaped path of destruction coming out from the main vent of the volcano. Then that kind of blew out all the chunks of the size of rocks. Then what we ended up happening is, up in here, gases and ash rose up into the atmosphere. Alright. On our long day, we're going to watch a video about another famous volcano called Krakatoa, which is in Southeast Asia. And after that's done, we will hopefully have time to watch a little bit of the Mount St. Helens footage. So, pyroclastic material comes in many shapes and sizes. There are the really small ones, which are less than 2 millimeters in diameter. Tinier than that little red dot I just put there. Alright, that's called volcanic ash. And if you have that ash less than 1/4 of a millimeter in diameter, we call it volcanic dust. And that's what's covering the cars in this picture. It's volcanic ash and volcanic dust. And this stuff can hang up in the atmosphere for years. As we get bigger, if you have pyroclastic material that is around the size of a dime, less than 64 millimeters or 6.4 centimeters, we call that lapilli. It's a little bit bigger than the dust. As we get bigger still, this is above 6.4 centimeters, above 64 millimeters, we call these objects volcanic bombs. And they get thrown out. A lot of times it's lava to start with. It's liquid thrown out, a big clot of lava getting thrown out of the volcano, and then it cools in the air to develop a round or spindle or football shape, like you see in many of these. The thing about the pyroclastic material is as you go from the ash to the dust, or the dust to the ash to the lapilli to the blocks, and now these really big ones called blocks after the bombs, these large solid pieces, you find the bigger pieces closer to the volcano. Alright, so the big pieces are close to the volcano. And that's because it takes so much more energy to throw them through the air. Something like volcanic ash or dust can float up in the wind and maybe get carried hundreds of miles away. Whereas something like these ridiculously huge sized volcanic blocks, or even the slightly smaller volcanic bombs, are a lot heavier, so they tend to fall down to the earth quicker, so you get more blocks and bombs close to the volcano, and you get a lot of ash and dust that can travel farther away. And the lava flows and the pyroclastic material, after several eruptions, it starts to build up, and they build up around the vent. Remember, the vent's the hole in the lithosphere that allows the magma to come up, and we get what are known as volcanic cones. And up near the top of the volcano, we have the crater. And usually what ends up happening is that crater becomes wider as weathering and erosion happen. And what happens is that the edges of the crater start to wear away, and then sometimes the crater falls in on itself and could even collapse into the vent, which could cause pressure to build. Which would lead to another violent eruption. So the way in which these volcanoes are formed, or the way in which the pyroclastic material and the lava build up over time, give rise to 3 different types of volcanoes. The first are the shield volcanoes, and the big thing about the shield volcanoes, you gotta think of a shield like a knight would carry. It's just large and broad and pretty flat. They're not that steep. The Hawaiian Islands are an example of shield volcanoes, and they tend to come from mafic volcanoes or quiet eruptions. Cinder cone volcanoes are your classic volcanoes. You can see they have a steep slope compared to the shield, which has a slope that is much flatter. Cinder cones tend to have this nice cone-shaped crater in the middle, but they don't end up getting all that high, a few hundred meters high, so maybe 1,000 feet high at the largest ones. And they form from explosive eruptions, and they get made from pyroclastic material. And then there's the composite volcanoes. And the composite volcanoes come from eruptions that are sometimes quiet, sometimes explosive. So when explosive eruptions happen, there's lots of pyroclastic material. And then a quiet eruption happens, and lava flows to cover the sides. And then it explodes and sends out chunks of that cooled lava as volcanic bombs and volcanic blocks. And it happens over and over again. These are also known as stratovolcanoes. And as we'll see in the Krakatoa movie, Krakatoa was a stratusvolcano, as well as Mount St. Helens is a stratovolcano. It has these alternating patterns of quiet and explosive eruptions. When the magma chamber is where the magma builds up in the volcano, when that empties during an eruption, alright, it partially empties during an eruption. a bunch of mass and weight is released or taken off of the ground, and so the ground starts to sink, and that's part of the reason for that is there's nothing supporting it underneath anymore. And so if you have a really big eruption with lots of magma, we can get a big caldera to form, and sometimes calderas filled with water to form lakes. It's just this big depression in the earth, in the crust, and then it fills up with water, and we end up with a lake. Now, as far as predicting volcanic activity, it's not something we're great at, but we have noticed a couple of things. There are some important warning signs of volcanic activity. One are earthquakes. As you have more magma moving up, it could be changing stuff around, melting other rock, and you can get shifting happening under the earth. And generally, we see an increase in the strength and frequency of earthquakes. Alright? Don't worry about this remember complex sine waves thing. That's from years past. But pretty much as you have a couple of earthquakes happening close together, the seismic waves from those earthquakes can combine. And it can be a signal of eruption, which is what the earthquake in May of 1980 did signal. And in fact, it triggered that landslide that then pretty much uncorked Mount St. Helens. Alright, the other big thing, another thing to see before an eruption, is you might see this bulge. So here was Mount St. Helens in the 1970s, and this was May 1980. And what you can see is this big bulge. I mean, this is the same mountain. This is way before the eruption, before the magma really started piling in, and then so much magma and gas got built in, it was trapped by all this solid rock, that it just started to push that rock, and eventually all this rock right here in this circled area slid down the mountainside right before the eruption. The other thing we can look at is we can look at surface temperature of the rocks. As the rocks get hotter, the magma is getting closer, and also gas emissions. As there's more gases being released, there's more magma coming in, bringing those gases with it, and see that. The downside is that we've only studied a few active volcanoes, so we're very early on in this whole process of coming up with really reliable predictability and activity patterns of volcanoes. So as usual, if you have any questions, please bring them with you to your next class, and I hope you like talking about volcanoes. Have a good night.